Hey everyone, my name is Vernon Dsouza. I'm a lead software engineer here at Velotio Technologies. My expertise includes media and streaming applications, audio codecs, and embedded firmware. So we are going to look at the trade-off between audio fidelity and codec performance. You may have noticed your favorite song has a different feel if you change the audio system used for playback. This is because of the design of the speaker hardware and also due to the audio processing firmware. We are going to look at how the firmware design attempts to balance performance and audio fidelity. So let's get started. Let's understand some of the points that we will cover. We experience a lot of variation as part of a music listening experience over many different speakers. For one, this can be attributed to the speaker characteristics. Another is a reduction in audio fidelity. Audio fidelity is highly sought after, but there are certain conditions which affect it. One would be the techniques used to optimize audio codecs, which we will discuss with respect to ARM architecture. Once we understand how software optimizations affect the original audio signal, we will briefly look at psychoacoustics, which will help us evaluate this change. Let's understand some factors affecting audio fidelity. Through audio fidelity, we understand how accurately a reproduced audio signal resembles the original sound source. Every speaker has a unique sound profile or frequency response. This inadvertently affects the audio signal. It is also the reason you hear people describing audio from one speaker as warm and another as bright. An audio codec is a piece of software that manages the compression and decompression of audio samples for efficient storage and transmission. We all know embedded platforms have limited processing power. This makes it necessary to tweak the codec performance to enhance the user experience. Here we have some examples of embedded devices with multimedia capabilities. You are all familiar with smartphones, tablets, smart speakers, and MP3 players. These mostly use the ARM processor as it contains a lot of special features to speed up multimedia applications. Here we see a wider range of ARM-powered embedded devices. You may have owned quite a few of them. We are going to continue the performance-related discussion with respect to ARM embedded platforms as they dominate the consumer electronics market. This is an audio spectrogram of a file compressed with two different audio codecs. The one to the left is compressed using FLAC, a lossless codec, while the one to the right is compressed using MP3, a lossy codec. The FLAC file is able to preserve audio frequencies right up to 20 kilohertz. This is a threshold of human hearing. However, the MP3 file cuts off frequencies at around 18 kilohertz. This is because lossy codecs allow discarding of some inaudible audio data, and this leads to better compression. Thus, the compression method we select can affect audio fidelity. FLAC being lossless does not reduce any audio fidelity, but lossy compression techniques like MP3 and AAC lead to a trade-off between audio fidelity and compression. We can leverage this concept when we attempt to improve performance, especially for lossy codecs. For lossy codecs, we can discard some non-consequential audio data to improve the performance. For lossless codecs, however, we need to manage the speed up without introducing any change to the audio bit stream. Let's now consider a case study to understand why we need to optimize audio codecs. Let's say you purchase a voice-controlled speaker, but on a tight budget. The low cost is possible as it utilizes a less powerful, hence cheaper processor. There's a high possibility the responses to your voice commands may be slow, and you may experience audio pauses from time to time. This trade-off is expected, as it is performing complex computations with constrained resources. So now, what can you do about this? You could try updating the firmware to its latest version. And you may find all these problems are taken care of. That's the power of using the processor resources efficiently through software optimizations. Now let's understand what makes ARM optimization so special. We usually focus on optimizing algorithms by reducing their time complexity. This technique improves performance irrespective of the underlying architecture. When we optimize for ARM, we harness unique capabilities of the ARM architecture to achieve better performance. Let's look at some features of the ARM architecture. The ARM architecture is designed to optimize code in a number of ways. Most ARM instructions can be executed in a single cycle. ARM has multiple execution units like the ALU and MAC, both of which can operate in parallel. This increases instruction throughput. Transforming audio data involves a lot of data-intensive operations. Data processing follows a load store architecture. As per this, we will only work on data after moving it to the register bank. It will then be moved back to storage once we are done with the processing. This will help reduce memory access latency. The pipeline architecture that we see to the left divides instruction execution into 3 stages: fetch, decode, and execute. This allows multiple instructions to be in various stages of execution simultaneously. We need to fetch the add instruction from memory and decode it before it can be executed. Looking at the diagram, we see this is happening, and we also see the subtraction instruction is going through the same process the moment the relevant pipeline stage is free. To the right, we see a diagram of parallel computations being done in a coprocessor. A coprocessor is a specialized processing unit designed to work alongside the microcontroller. It helps us speed up digital signal processing tasks for audio and video. What we see here is an example of ARM's Neon SIMD instruction set performing parallel additions. To speed up the code, we need to understand what a processor spends its time doing. If you look at any ARM assembly code, you will see the following. Most of the time is spent in data movement, control flow, and math calculations. Improving our code for these operations will have a large impact on performance. Let's look at some optimizations for audio codecs. Audio codecs convert integer audio samples into compressed audio data and back as smooth and fast as possible. We can structure audio samples such that they can be transferred to and from memory in an efficient manner. Parallel computations via SIMD speed up math operations. Instruction scheduling maximizes the utilization of the different ARM execution units. Loop unrolling is extremely useful to speed up repetitive operations on large blocks of audio data. Reduction in precision of integer values is a very useful optimization technique. ARM's design is geared towards parallel math operations on small data sizes. Faster processing can be achieved by reducing the precision of integer values. In the diagram to the left, we see the Neon coprocessor can work on 8, 16, 32, and 64-bit data types. In the diagram to the right, we see it processing 4 16-bit values in parallel, achieving more speed. This reduction in precision results in a loss of some audio fidelity. We need to strike the right balance between performance gains and audio quality. The waveform in front of us shows the change in the original audio signal due to a reduction in precision. If our optimizations are well implemented, this change in audio fidelity will be barely noticeable. There will only be a change in subtle audio nuances and fine details. But let's understand how we evaluate this change. For that, people use psychoacoustics. Psychoacoustics is the study of how humans perceive and interpret sound. It delves into how the brain processes auditory information. Any change to audio fidelity will be judged in terms of a psychoacoustic model. It gives us a clear idea if our optimizations have only affected audio data, which is inaudible or insignificant. For example, a change in precision may just cause a further reduction in amplitude or minor changes in frequency for inaudible audio components. In conclusion, audio fidelity is a highly desirable feature, but performance constraints of embedded platforms force us to accept some level of compromise between the two. No matter the approach, audio fidelity and performance remain a delicate balancing act.